Welcome back again. In our last video, we have discussed Faraday's law of electromagnetic induction, coil-coil experiment, coil-magnet experiment, coil-coil experiment with Plucky, and uh, Lenz's law. Today, we will discuss motional EMF or motional electromotive force. EMF means electromotive force. Let us discuss this motional EMF. Okay. So name itself indicates motional EMF. That means current is induced due to the motion of the conductor, or current is produced, generated due to the motion of the conductor. Okay. How it is possible? Let us discuss this one. Observe the diagram here. In this diagram, P, Q, R, S is a rectangular conductor. So PQRS is a rectangular conductor in which this PQ is a straight conductor which is movable, whereas these parts are fixed. Only this part is possible to move. Okay. Now this rectangular conductor is placed in a uniform magnetic field B, means this which I have shown with a cross mark here. This conductor is placed in a uniform magnetic field. Okay. Now, when this conductor moves, that moves towards the left, and this moves with the velocity v. Therefore, I have written let v be the constant velocity of this conductor when it moves. Okay. So what you have to write here? Let us consider a rectangular conductor PQRS placed in a uniform magnetic field in which the conductor PQ is movable. Okay. Now we have to derive the expression here. How the EMF is induced due to the motion of the conductor. I have to derive the expression for EMF E. Okay. So let us consider this distance RS as L and this distance RQ as X. So let RQ is equal to X and RS is equal to N. This PQRS now forms a closed loop. In a closed loop, the magnetic flux induced is phi B. So in our last video, we have discussed the magnetic flux in case of Faraday's laws of electric induction, that is phi B is equal to B dot A or BA cos theta. So here the maximum flux is produced due to when theta is equal to 0, cos 0 is 1, therefore phi B is equal to B dot A. Now how this flux becomes here? In this diagram, B is same, B is magnetic field only. Now what is the area? Area is length into breadth, length into breadth. Length is here L, breadth is here X. So instead of area, I will write this one as Lx. So B into L into X, because A is equal to L into X. So therefore phi B is equal to B into L into X. Induced EMF E is equal to, we have seen from the Faraday's law of electromagnetic induction, E is equal to minus d phi B divided by dt. Okay, minus d phi B divided by dt. Now we have just now calculated the value of phi B. Just substitute that value of phi B here. This is equal to minus d phi B is what? BLX, BLX divided by dt. This is induced EMF E. Now, I will take this BL outside. It is BL minus dx divided by dt. So, this is equal to minus BL. So, what is dx divided by dt? Rate of change of displacement is velocity. Or rate of change of distance is. speed. So BLV. So this E is equal to minus BLV, or if you take V is equal to minus dx divided by dt. So this becomes plus V is equal to minus dx divided by dt, because the conductor is moving in this direction with a speed V. Therefore, E is equal to BLV is the expression for induced EMF, which is called motional EMF. So, motional EMF E is equal to B into L into V, where V is minus dx divided by dt. Thus, we are able to produce the induced EMF by moving the conductor instead of varying the magnetic field. It is also possible to explain the motional EMF by considering the Lorentz force. So here, Lorentz force we have studied in the previous chapter. See here, let us consider an arbitrary charge Q on the conductor PQ. When this conductor moves with the speed V, the charge will also move with the speed V. Now, in a magnetic field B, the charge moves from P to Q, that is in magnitude and direction is from P to Q. Therefore, while the charge moves from P to Q, work is done. Therefore, that work is equal to force into displacement. Now, what is the force? Force into displacement. The force is, Lorentz force is here, F is equal to, if Q is the charge, V is the speed, in a uniform magnetic field, F is equal to Q into V into T. Okay, so the force is QVB into the displacement. So here, moving from P to Q here, the length of this one is L. The same length is considered here because opposite sides are equal in a rectangle. Here this is a rectangle. Okay, therefore displacement is L. This is equal to QVB into L. So QVB L is the, this is the work done. Now we want E, that is the induced EMF. According to the definition, E, this is equal to work done per unit charge. Work done per unit charge. Work done per unit charge is E. Therefore, we have to substitute the value of W here. W is equal to Q into V into L divided by Q is E. Q getting cancelled. E is equal to BVL, or the same thing I write BLV. So here also we have got the same expression. Induced EMF E is equal to BLV. Here also induced EMF E is equal to BLV. This is the ultimate method by considering the Lorentz force here. So both the expression is same. Therefore, the expression for induced EMF is B into L into V. Thus, it is possible to produce induced EMF by the motion of the conductor instead by varying the magnetic field. Okay. Now, in case of stationary conductor, if the conductor is stationary, it is not moving, then the expression for the force F is equal to Q into E plus V into V. Okay, so here V is equal to 0 in case of stationary conductor, V is equal to 0. If V is equal to 0, F is equal to Q into E only. This part becomes 0. Therefore, F is equal to Q into E in case of stationary conductor. Now, let us discuss energy consideration, that is a quantitative study. Already we have discussed the Lenz's law, a qualitative explanation, but here we will discuss the quantitative explanation of this one. The Lenz's law is inconsistent with the energy conservation. Okay. Now here small r be the resistance of this movable arm PQ, whereas the arm RS, SP and RQ have a negligible resistance. smaller. But only PQ is having the resistance. The movable arm is only having the resistance R. Let I be the current on this loop, closed loop PQRS. Okay. Now, on account of the presence of magnetic field, there will be a force on the arm PQ, and this force is directed outward in the direction opposite to the velocity of the rod. That means this PQ is placed in a uniform magnetic field. On account of this magnetic field, there will be a force on this arm due to the magnetic field B. Then this force is directed outward in the direction opposite to the velocity of the rod. Therefore, that force F is equal to I into L into B. Now, what is I? I we have to calculate. According to this, I is equal to E divided by R. I is equal to E divided by R, and just now we have derived E is equal to induced EMF E is equal to BLV divided by R. Okay, so this BLV divided by R we have to substitute here. I is equal to B into L into V divided by R, and again L into B. So this is equal to B into B is B square, L into L is L square, V divided by R is F. F is equal to B square L square V divided by R. Alternatively, we can derive this one. When this arm is pushed with a constant speed V, then the power is dissipated. The power required to do this is power P is equal to F into V, where this F is equal to here B square L square V divided by R into V is P. This is equal to B square L square V square divided by R. P is equal to B square L square V square divided by R. And we know another relation. The agent that does this work is mechanical. See here, we have studied in the last discussion, we have studied that in the coil magnet experiment. So here this coil is there, and this is connected to a galvanometer G, and a magnet is there here. When this magnet is moved inside the coil and away from the coil, the magnetic field is created, and due to the magnetic flux is induced. Due to this one, it induces an EMF in the coil. See here, while this magnet is moving towards and away, this is due to the mechanical energy, because of mechanical energy, and here this mechanical energy is converted into electrical energy, and due to this electrical energy, when the current flows through the coil, due to this one, this coil gets heated, means thermal energy. Thermal energy. That means it clearly shows that mechanical energy is converted into electrical energy, and this electrical energy in turn is converted into thermal energy. So the energy is conserved. So it is converted into one form to another form. It will not lose. So energy is, this is energy conservation. So that is, energy is converted from mechanical to electrical and electrical to thermal. So there is no loss of energy. Energy is conserved here. Now this dissipated heat is given by P is equal to I square into R. This relation I square into R. So here I is, just now we have calculated I is equal to BLV divided by R into R is there. Okay, BLV divided by R whole square into R. So this is equal to B square L square V square divided by R square into R. R will be cancelled. So this is equal to B square L square B square divided by R is P. B square L square B square divided by R is P. So both the expressions are same, right? So this is the quantitative explanation of the energy consideration. Now there is one interesting relation between the charge flow through the circuit and the magnetic flux. Let us discuss that one. We know that from the Faraday's law, of induction, Faraday's law of induction, we know that the magnitude of EMF E is equal to d phi b divided by dt. I write delta phi b divided by delta t. So magnitude, I have taken the magnitude, so minus, I have not written, magnitude of E is equal to delta phi b divided by delta t. However, we know that this EMF, in the previous chapter we have studied that this is equal to I into R. This EMF is equal to I into R, drift velocity I into R. So this is equal to delta phi b divided by delta t. And this I is equal to, you know that this I is equal to rate of change of charge delta q divided by delta t. Delta q divided by delta t into R is equal to delta phi b divided by delta t. Now what is delta q? We got the relation between delta q and delta phi b. Both are there here. Just you take this one, delta q is equal to, take out this one towards that side, delta phi b divided by delta t, and I take this delta t here divided by R. Right? Delta t getting cancelled. So delta q is equal to delta phi b divided by R is the relation between the charge and the magnetic flux, where phi b is the magnetic flux and R is the resistance. Okay? Let us solve one problem. Here a wheel with 10 metallic spokes, each 0.5 meter long. The length of that spokes is 0.5 meter. That is rotated with a speed of 120 revolutions per minute, not in second. 120 revolutions per minute. For 1 minute it will rotate 120. In a plane normal to the horizontal component of the Earth's magnetic field. So this will rotate in that plane such that it is normal to the horizontal component of the Earth's magnetic field. Horizontal component of the Earth's magnetic field, if it is like this, then this is rotating like this, perpendicular, normal. Okay, if HE is equal to 0.4 G, G means Gauss. The HE means horizontal component of the Earth's magnetic field. In some book they may take B. So horizontal component BH, 0.4 Gauss, and there are given 1 Gauss is equal to 10 raised to minus 4 Tesla. At the place, what is the induced EMF between the axle and the arm of the wheel? So you have to calculate the induced EMF. So here you use the formula induced EMF is equal to half omega B R square. Half omega B R square. Now how you get this expression? Can you try? Just I will give simple clue. That means here you take that DE is equal to, you know that B into L into V, BE, L is the radius dr. DE, EMF induced is equal to B into V into dr. Now you get the EMF induced is equal to integration of DE. So integration of DE, you do this one with respect to R. Integration from 0 to R. You do this one, finally you get this expression. So you know one relation, that is V is equal to R omega. Another relation also you know. Substitute this one here. Then taking the common and integrate with respect to dr. Finally you will get this expression, and after that you substitute all these values. Let us solve this problem. A wheel with 10 metallic spokes. A wheel is there. A wheel. This is the center. 10 metallic spokes are there. How much? 1, 2, 3, 4, 5, 6, 7, 8. Another 2 I will draw. Like this, 10 spokes are there. A metallic wheel with 10 spokes. This is the center. With the length L, each spoke is having the length L, and that length is given as 0.5 meter. Length L is equal to 0.5 meter. These are the given quantities. 0.5 meter. And here this rotated with a speed of, this is omega. This rotates with a speed of 120 revolutions per second. That means omega is equal to 120 revolution per minute. You have to convert this into radian per second. So this is equal to 120 into 2 pi radian, 1 revolution. This is 2 pi radian, and 1 minute is equal to 60 seconds. So 2 pi by 60 radian per seconds. 60 ones are 62s are. So this becomes 2 into 2 is 4. 4 pi radian. So omega is equal to 4 pi radian. And next also they have given this is rotated perpendicular to the plane of the magnetic field. That means B is the magnetic field. This is rotated perpendicular to the field. This wheel rotated with a speed of 120 revolution per minute in a plane perpendicular to the horizontal component of the magnetic field, and that horizontal component of the magnetic field is BH, but here they have given this one as HE. HE is same as BH. So this is equal to 0.4 Gauss they have given. Convert this into Tesla. 0.4 into 10 raised to minus 4 Tesla. Now we have to calculate the EMF induced. Okay. So find out the value. The answer for this problem is 6.28 into 10 raised to minus 5 volt. 6.28 into 10 raised to minus 5 volt. So this answer you have to get it. Okay. Let us solve this problem. In this problem, a metallic rod of 1 meter length is rotated with a frequency of 50 revolutions per second. A metallic rod of 1 meter length. A metallic rod is there. This is of 1 meter. Length of this rod is 1 meter. Is rotated with a frequency of 50 revolutions per second. That means in 1 second it will rotate 50 times. With one end hinged at the center and the other end at the circumference of the circular metallic ring. That means one end of the rod is at the center of the circle and the other end of the rod is at the circumference. Means this end is at the circumference. So that means this is the center and this is the circumference of the circle. Like this. That means it indicates this from center to the circumference. We can call this one as a radius. Therefore, radius itself is the length of the rod. That means we can write the given value of the length of the rod as R. Given L is equal to R is equal to 1 meter. Okay. And the frequency is 50 revolutions per second. F is equal to 50 revolutions per second. Then a metallic ring of radius 1 meter about an axis passing through the center and perpendicular to the plane of the ring, and constant and uniform magnetic field 1 Tesla, that means B is 1 Tesla, this is parallel to the axis, is present everywhere. That means this should be, field should be inside. That means this is parallel to the axis of this one. Magnetic field is parallel, and we have to calculate what is the EMF between the center and the metallic ring. What is the EMF between this center and this metallic ring? So you have to calculate the value of the EMF. Now we have studied the formula for the EMF, and that EMF of a rotated disc. There we have studied EMF E is equal to half B omega R square. This formula that we have already studied. So this is equal to half into B value is given as 1 Tesla into omega. So omega value is not given here. Instead of omega they have given F. If you know the value of F, you can easily calculate omega. Omega is equal to 2 pi F. So this is 2 pi into F is 50 revolutions per second. So 50 into 2 is 100 pi. Omega is equal to 100 pi. I substitute this omega as 100. So 100 pi into R value is 1 meter. So 1 meter. So 1 meter. This is square. Square. Now 2 ones are 50s are. So this is equal to 50 pi. Answer is EMF of this EMF between the center and the metallic ring is equal to 50 pi. Clear? See here in this problem, a long solenoid with 15 turns per centimeter has a small loop of area 2 centimeters square placed inside the solenoid normal to its axis. If the current carried by the solenoid changes steadily from 2 to 4 amp in 0.1 second, what is the induced EMF in the loop while the current is changing? So let us solve this problem here. They have given a long solenoid with 15 turns per meter. That means a long solenoid, I draw here a long solenoid . 15 turns you have to draw. Now long solenoid of 15 turns per meter means 15 turns N is equal to 15, but turns per centimeter is there. That is, it is N by L. N by L, you know this one as small n. Small n is equal to N by L. 15 turns per centimeter is given. Convert that into meter. So this is equal to 1500 turns per meter. Because 1 centimeter is equal to 10 raised to minus 2 meter. So 15 divided by 10 raised to minus 2. When 10 raised to minus 2 goes up, this becomes 10 raised to plus 2. 15 into 10 raised to plus 2 is 100. 15 into 100 is 1500 turns per meter. So here the long solenoid with 15 turns per meter and has a small loop of area. It has a small loop here inside. Small loop inside the solenoid is given there. Small loop is inside. Normal to its axis. Normal to its axis. That means the field direction. This is the axis. This is placed the normal to the axis. Then the field direction is this one. Area vector is also along this direction. Okay. Normal to its axis. If the current carried by the solenoid changes from 2 to 4 amp, current changes from 2 to 4, starting it is 2, finally it is 4, then the change in the current di is equal to 4 minus 2, this is equal to 2 amp. Change in the current, final minus initial. So in the 0.1 second means dt is equal to 0.1 second. Okay. What is the induced EMF in the loop? You have to calculate the induced EMF E. Now you know the formula induced EMF E is equal to d phi divided by dt. E is equal to d phi divided by dt. Here d phi by dt, d by dt of phi is what? You know that phi is equal to the flux. Phi is equal to b dot a, or you can write this one as ba cos theta. Here this theta is equal to, as the field and area vectors both are in the same direction, they are parallel, therefore theta is equal to 0. Therefore this is equal to ba only. Cos 0 is 1. Therefore phi is equal to ba. So this is equal to EMF is equal to d phi divided by dt, and phi is equal to b into a. Instead of phi I will write this one as b into a. But here b value also we don't know, and also you know that another formula b is equal to mu naught n I. This also you know. So in this chapter only that we have studied, b is equal to mu naught ni. Therefore substitute this value here. D by dt, I take this a outside, a into d by dt of mu naught ni. Mu naught n also you can take it outside. Therefore mu naught ni a into di divided by dt is e. This formula will get. Now substitute all these values here. E is equal to mu naught value is 4 pi into 10 raised to minus 7. 4 pi into 10 raised to minus 7. And n value, shall I write this one? Into n value is 15 tons per centimeter. It is 1500 tons per meter. That is n is over I. Mu naught n a di divided by dt. A value is given as area. Area is also given. Area of the loop is 2 centimeters square, that I have not written. So area A is equal to 2 centimeters square. It is 2 into 10 raised to minus 4 meters square. They are here 2 centimeters square. It is 2 into 10 raised to minus 4 meters square. I write here 2 into 10 raised to minus 4 meters square. A is over di divided by dt. Di is the change in the current. It is 2m into 2 divided by dt value is 0.1 second. This is 0.1 second. So all the values direct problem it is. 1 you can write this one as 1 into 10 raised to minus 1. When 10 raised to minus 1 goes up, this becomes 10, and all these things you multiply. 4 pi into 1500 into 2 into 2 into 10 comes up. Okay. So what it becomes? Calculate this one. Simple calculation is this one. You can calculate this, and the final value I will write. That final value is 7.5 into 10 raised to minus 6 ohm. You do this calculation and verify this. Okay. In the next video, we will discuss the further part. Okay. Thank you.